Hi there. It's June 3rd, and before your exam, I'm taping Chapter 5, Chemical Quantities and Reactions, as this is one of the tough topics to truly comprehend, converting moles to grams and grams to moles. And next week, you'll be working in your groups and presenting the 8 sections as groups, showing what you understand about this chapter. So we will be doing a flipped classroom next week. So what is a mole? A mole is defined as particles or atoms or molecules or ions that have 6.023 times 10 to the 23rd atoms, oftentimes referred to as Avogadro's number. So if you write 602 with 23 different zeros, and as we learned in chapter 1, we would write this down in scientific notation and write it as 6.02 times 10 to the 23rd. So we can say a mole of an element has 6.02 times 10 to the 23rd atoms. A mole of carbon has also the same number of atoms, as well as a mole of sodium, a mole of hydrogen, a mole of potassium. And here's the relationship. So if we have a mole of aluminum, there are Avogadro's number of atoms of aluminum. If we want to write down a mole of water molecule, then there are 6.02 times 10 to the 23rd molecules of water. Or if we happen to look at a mole of sodium chloride, then we refer to it as formula units of sodium chloride that have 6.02 times 10 to the 23rd. So Avogadro's number can be written as an equality. 1 mole is equal to 6.02 times 10 to the 23rd, and from chapter 1 we've learned to write down conversion factors, 6.02 times 10 to the 23rd particles per mole, or 1 mole over the number of particles. So how do we go about calculating atoms or molecules? So first we want to learn how to convert, and here's an example. How many carbon dioxide molecules are in half a mole of carbon dioxide? So as we learned, we write down what is given, 0.5 moles of carbon dioxide. And what is our find? What do we need? Molecules of carbon dioxide. So we have a plan. We write down the conversion factor. And as we want to convert 5 moles of carbon dioxide into molecules, then we need to cancel the moles, and so our conversion factor would be multiplying it by Avogadro's number of molecules over the mole, and so we get 3.01 times 10 to the 23rd molecules of carbon dioxide. And so for our learning check, how do we go about finding the number of atoms? How many atoms are there in 2 moles of aluminum? So we write down our given, 2 moles of aluminum, and we need the number of atoms of aluminum. So now we need to write a plan.
I'm sorry.
This is your class going here? No. So we use the number of atoms, 2 moles of atoms, to write our conversion factor again, and write down our given, 2 moles of aluminum, and then use moles in the denominator so that we cancel 2 moles of aluminum, and we come up with the desired number of atoms. So you can continue practicing with the number of sulfur atoms. So how do we convert moles of elements in a formula if we have aspirin, acetyl salicylic acid? Aspirin has 9 carbons because it's C9, and there are 8 hydrogens, and there are 4 oxygens. So C9 H8O4 from the formula unit. So the subscripts, the relationship. So one molecule of aspirin has 9 atoms of carbon, or 9 moles of carbon, 8 atoms of hydrogen, or 8 moles of hydrogen, 4 atoms of oxygen, or 4 moles of oxygen. So we can write different types of conversion factors depending on the number of carbon atoms, hydrogen atoms, or of oxygen with respect to the number of moles. So then we want to have a plan. We want to convert moles of aspirin into atoms of oxygen. And by doing so, we come up with, as we are given, 0.15 moles of aspirin, and we need to find out the number of atoms of oxygen. We need to use a conversion factor where we have 4 moles of oxygen from the formula over 1 mole of aspirin to cancel out the moles of aspirin. And then to cancel out the moles of oxygen, we use Avogadro's number, 6.02 times 10 to the 23rd atoms of oxygen. And as we do the math, 0.150 times 4 times 6.02 gives us 3.61 atoms of oxygen. And as we start with 3 significant figures, so we also end up with 3 significant figures. Now let's go to section 5.2, the molar mass. How do we go about calculating the molar mass? The molar mass is defined as the mass of 1 mole of an element and can be referred to as the atomic mass if it's an element. So the molar mass of carbon would be 1.01, for silver 107.9, and for sulfur 32.07. So we tend to weigh and mass the elements that we work with in the lab. And so therefore we can say 1 mole of silver weighs 107.9 grams of silver, where 1 mole of carbon weighs 12.0 grams of carbon. Likewise, 1 mole of sulfur weighs 32.1 grams of sulfur. So how do we go about looking and finding the 1 mole of potassium atoms and its atomic mass unit? We will want to use our periodic table, and as we look down at the atomic mass unit in our periodic table for potassium, it's 39.1. And Sn is 108.17, and for Ca is 40.0 grams of calcium. So how do we go about calculating the molar mass of a compound such as C2H6O if there are 2 carbons, 6 hydrogens, and 1 O? So we know that 1 mole of carbon weighs 12 grams, 1 mole of hydrogen weighs 1.01 grams, and 1 mole of oxygen weighs 16 grams. So therefore, as there are 2 moles of carbon, we write down 2 moles times 12, and we would get 24 grams of carbon. Likewise, 6 moles times 1, 6.06 moles of hydrogen, and for oxygen, just 1 mole, so 16 grams of oxygen. And then the molar mass now of the compound C2H6, we just go ahead and add carbon, hydrogen, and oxygen masses to give us 46.1 grams of C2H6O. So mole quantities, therefore, are very unique measuring units, because we can convert grams into mole and moles into grams. So you could be asked, how will you find the molar mass of potassium oxide? So to find the molar mass of potassium oxide, you look at potassium, 32.91 grams per mole, but there's two of them, so you multiply it by 2. And there's only one oxygen, so you add 40 times 2 plus 16 to get your aluminum hydroxide. So here is our calculation for potassium oxide. 2 moles of potassium times 39.1 grams, you get 78.2, roughly 80 grams. And for aluminum oxide, there's only one aluminum, but we have 3 moles of oxygen based on the subscript, 3 moles of hydrogen. So we add that all together and we get 78 grams of aluminum hydroxide. As the molar mass of aluminum hydroxide, 94.2 grams of potassium oxide. And you can practice calculating the molar masses of different other compounds. So we can use molar masses as conversion factors also. So then, how can we convert the mass into moles? We learned how to convert moles into grams into mass. Now, let's learn to do the opposite. So if we're given a box of table salt is sodium chloride, and it has 737 grams of sodium chloride. How many moles are there? So then we want to think of a plan that we want to convert grams of chloride to moles of sodium chloride. So we know that 1 mole of sodium weighs 23 grams per mole, so that's 23 grams. 1 mole of chloride weighs 35.5 grams per mole, and so we add the two together to get 58.5 grams of sodium chloride. And to set up the problem, as we're given 737 grams of sodium chloride, then we use the grams of sodium chloride in the denominator to cancel out the grams, so we come up with our desired unit of moles, 12.6 moles of sodium chloride. So another learning check, garlic allyl sulfide is a compound. How many moles of allyl sulfide are in 225 grams? So that's our given, 225 grams, and we need to find out how many moles of allyl sulfide are there. So we know that there are 6 moles of carbon, 10 moles of hydrogen, 1 mole of sulfur. We add those together to get a total of 114.2 grams of allyl sulfide. So to set it up, to come up with a number of moles of allyl sulfide, so then we set up 225 grams of allyl sulfide times 114 grams of allyl sulfide to get our desired 19.5 moles of allyl sulfide. So let's move on to section 5.3, chemical reactions and equations. A chemical change occurs when one substance is converted into one or more substances with different formulas. So we want to highlight different formulas. For a chemical change, the formula changes. And so we may observe bubbles formation of bubbles, or change in color change, or a solid could be produced, as in this instance where we have silver tarnish. From silver to silver tarnish or silver sulfide with a formula of Ag2S. So visible evidence of chemical reactions are change in color, formation of gases, formation of a solid, or the production of energy in the form of heat. This example is just a chemical reaction when iron is left out and exposed to, say, the atmosphere, and we see the grayish iron nails turn into rust, which is Fe2O3, or is oxidized. So which would represent a chemical change? Is it a burning candle, ice melting, the burning of toast, or turning water to steam? The only chemical changes are the burning of a candle and the burning of toast. Ice melting and water turning into steam are physical changes, changes of state. So how do we write chemical equations? Chemical equations come in the form of carbon plus oxygen gives us carbon dioxide. So we learned that matter can neither be created nor destroyed. So the starting materials, carbon and oxygen, we should have the same amount of starting materials in the form of carbon and oxygen, and the same amount of products in the form of carbon dioxide. So reactant atoms and product atoms have to be the same. So how do we go about balancing a chemical equation? So how does aluminum sulfide form? So we take aluminum and react it with sulfur, and we form aluminum sulfide. But we see that there's only one aluminum in our reactant, but then there are two aluminum atoms in Al2 because of the subscript 2. So how do we go? And then only one sulfur atom, but then three. So what is the best way to balance this? We first have to use coefficients in front of aluminum. So because this has 2, so we want to put 2 in the reactant so that now the aluminum atoms are balanced. And then because this is S3, so then we put 3 in front of sulfur to balance the reactants with the products. And so more learning checks that you'll be discussing in class, but I'm just going over some examples for you. Balancing equations with polyatomic ions involves a slightly different procedure. We learned that polyatomic ions such as phosphate are covalently bonded, so they do dissociate as phosphorus or oxygen. But the ionic compound sodium phosphate dissociates as sodium ions, positive ions, and phosphate anions. Since we know from the periodic table that sodium tends to have a +1 charge and the phosphate has a 3-, so the formula for sodium phosphate would be Na3PO4. So in the reactants there are 2 PO4. If we want to put 2 as a coefficient, and then for the products, then we also see for Na, because it's Na3, so then we want to write down 3 in the NaCl. So Na is 6 and 6, and then because magnesium chloride, magnesium ion, and we have Mg3PO4, so we have a double displacement reaction. The sodium reacts with the chlorine to form sodium chloride. Magnesium reacts with phosphate to give you magnesium phosphate, which is a solid. And so to balance the equation, we need to put, if we put 6 already for sodium and balance the sodium, then we have also, then all we need to do is put a 3 in the magnesium chloride, the coefficient, the number before magnesium chloride to balance out both magnesium and the chloride ions. So then as we go to 5.4, the types of reactions. A chemical reaction can be classified as a combination reaction, a decomposition reaction, so combining, decomposition, single replacement, double replacement, or combustion reactions when compounds react with oxygen. So here's a combination reaction, but when it reacts with oxygen, it's referred to as a combustion. But for these some examples of combination reactions, when two or more reactants combine to form a single product. So we have two reactants here to form a single product, AB. So A plus B gives us AB. So a combination of magnesium and oxygen. So here's a magnesium ribbon. And as it combines with oxygen gas, we form a grayish substance called magnesium oxide with an intense white light or heat also being released. Decomposition reactions is when you have a substance, AB, splits or breaks down, decomposes or splits up into two or more products. So we have HGO turns into Hg plus O2. We have KClO3 breaks down into KCl and oxygen. So the decomposition of mercury involves mercurous oxide involves 2 hydrogen, 1 oxygen. Potassium chlorate, decomposition of 2 moles of potassium chlorate gives you 2 moles of potassium chloride and 3 moles of oxygen gas. And here is a schematic or nice drawing of it. Single replacement reactions is when you have zinc, one element, and a compound like hydrochloric acid, Bc. Zinc replaces hydrogen to form zinc chloride, and so that's referred to as a single replacement. Single replacement reaction. An element replaces a hydrogen. In this second example, iron replaces copper, so instead of copper sulfate, we have iron sulfate and we form copper metal. And here's a schematic of that. Double replacement now is when you have silver nitrate, A and B, and sodium chloride, C and D, forming, so the positive cation silver will react with the chloride and ion to form a solid precipitate, silver chloride, while sodium nitrate just stays as Na plus and then NO3 minus in solution or an aqueous solution. Another example would be zinc chloride, but then we form H2S, rotten egg gas. And we've also seen how we can have a double replacement reaction with barium sulfate when we react sodium sulfate with barium chloride. And once again, remember that when we react, say, methane gas with oxygen and gives out carbon dioxide and water plus a lot of energy, we refer to that as a combustion reaction. So the insert shows the balanced reaction between our propane, and then we're applying heat, right, with oxygen, so to form CO2 plus H2O. So propane, a very highly flammable gas, can be used to grill meat poultry, or fish. So how do we go about identifying different types of reaction? So an element plus a compound gives you a single replacement reaction. Two compounds, two ionic compounds give you a double replacement. Nitrogen plus oxygen gives you a combination. And then ethane gas plus oxygen to give you CO2 plus water gives you a combustion reaction. So how do we go about determining mole relationships in chemical reactions? And that's a topic for section 5.6. What do we mean by mole relationships? The law of conservation of mass says that matter can neither be created nor destroyed. No change in total mass occurs, so the mass of products need to equal the mass of reactants. Here are some examples of reactants: 2 silver, sulfur, and silver sulfide. So when silver and sulfur react to form silver sulfide. So in the equation, if we have 2 silver atoms reacting with sulfur atoms to form silver sulfide, in a sense, we have 2 moles of silver reacting with a mole of sulfur to give you 1 mole of silver sulfide. So 2 times 107.9 grams of silver plus 32.1 grams of sulfur, or 247.9 grams of combined grams of silver and sulfur, gives us also a total of 249 grams of the product silver sulfide. Another example could be the reaction between 2 moles of iron with 3 moles of sulfur to give us iron sulfide. So 2 moles of sulfur with 3 moles of sulfur, 2 moles of iron gives us Fe2S3. So on a mole-to-mole factor, we can say there are 2 moles of iron for every 3 moles of sulfur, or 3 moles of sulfur for every 2 moles of iron. And likewise, we'll do the conversion factors as we learned in chapter 4 and apply these same concepts in chapter 5. So how many moles of iron oxide can form 6 moles of oxygen? So first we want to make sure that the reaction is indeed balanced. And we know that we want to know how many moles of iron oxide from 6 moles of oxygen. So we're given 6 moles of oxygen, and we use a mole factor of 2 moles of iron oxide per moles of oxygen. We cancel out the moles of oxygen to give us the 4 moles of iron oxide. And for a learning check, another example, how many moles of iron are needed for the reaction of 12 moles of oxygen? Now let's go to 5.7, mass calculations during chemical reactions. If we want to determine the mass of ammonia from 32 grams of nitrogen, so we're combining nitrogen plus 3 moles of hydrogen to give us 2 moles of ammonia gas. So we'll write down our equivalent of 1 mole of nitrogen gives us 28 grams of nitrogen. Write down the conversion factor. Write down our given first, 32 grams of nitrogen. Right, here's our given. And then write down the conversion factor to cancel out the grams of nitrogen, and we end up with our 1.1 mole of nitrogen. See how easy that is? Another example. would be to determine how many grams of oxygen are needed to produce 45.8 grams of iron oxide in the following reaction. So first we need to make sure that the equation is balanced, right? There are 4 iron, 2 times Fe2 gives us 4. There are 6 oxygen, 2 times O3 gives us 6. So we set up the molar ratio. We want to cancel the grams of oxygen because we're given 45.8 grams of oxygen using dimensional analysis. We come up with 0.287 moles of iron oxide. And then we need to identify how many moles of iron are needed to form 12 moles of oxygen. So find the right conversion factor. And so we are given 4 moles of iron gives us 3 moles of oxygen. And so therefore, when we write down 12 moles of oxygen times 4/3 gives us 16 moles of iron. So the answer would be 16 moles of iron, which would be letter C in the equation. Okay, and that's it for the PowerPoint lecture for Chapter 5. And when I see you next week, we will be doing the lecture on. You will be doing the lecture. We'll be having a flipped classroom. Thank you.